Good morning, guys. Welcome to Friday. Hope everything went well with the midterm yesterday. Sorry I can't be with you guys, but I'm with you in spirit, so don't worry about it. Today, what we're going to do is we're actually going to start an introduction into circles. All right, so we've been kind of finishing up with triangles and everything else, and we're going to look at circles today. So the first part of what we're going to look at are just some basic properties of some circles, some of which you guys probably already have heard of, some other things you may not have. So if you guys just look at this first picture here, we're going to go through and just talk about some basic segments that occur in circles. So this first one, as you guys see, is a chord. It's not chord, it's actually pronounced a chord. But the key here, guys, is the fact that this is a segment. You guys can kind of see this is a segment, I know, nice and pretty and colorful, whose endpoints, and that's another key. Remember, guys, segment has endpoints to it. It does not keep going. It actually stops. Now, the key here with a chord is that it's a segment whose endpoints are on the circle. So it starts and ends on the circle. So if you guys take a look right here at segment AB, all right, right here, that is a chord because its endpoints occur on the circle. All right, so that's what a chord is going to look like. All right, so another thing that we're going to look at is called a secant, not a second, a secant. Now, a secant is a line. Now, it can be a segment, it can be a line, it can be a ray. But the key with the secant is it touches the circle twice, but it keeps going. All right, so a secant right here. So if we look over to our picture, we'll keep our highlighter here. All right, so this right here, so notice this is a secant. Now, if you notice, just like the chord, it touches the circle twice. However, unlike the chord, it keeps going outside of my circle. So it hits the circle twice like a chord, but it keeps going. So it could be a line, it could be a ray, it could be a segment. But a secant touches the circle twice, but keeps going outside the circle. All right, so that's a secant. Now, the last thing that we're going to look at, the last type of segment, line, array we're going to look at is called a tangent. Now, tangent you guys may be familiar with tangent and triangles, the trig ratio opposite over adjacent. However, this is tangent with circles. So we're actually not using any trig ratios here. It's just a different type of tangent. So similarly to a secant, it's a line. It can be a segment. It can be an array. But the key with a tangent is that it is only going to touch the circle one time. It's only going to touch the circle at one point. The point that it intersects that circle at is called the point of tangent. So it's kind of already highlighted there for you, but just to kind of reiterate it. All right, so a tangent hits the circle one time, and it hits the circle at the point of tangency. So chord is a segment that whose endpoints will lie on the circle. A secant is a line, segment, or ray that touches the circle twice but keeps going. And a tangent only touches the circle one time, and it touches the circle at the point of tangency. So there's some basic lines and segments about circles. So let's go on to our next slide. All right, so here we're going to identify some other basic segments, lines, or rays with a circle. All right, so some of you guys may be familiar with something called a diameter. Now, a diameter is a special type of chord. It's a special type of chord, though, that goes through the center of a circle. Every circle, if it's a perfect circle, has a center. All right, in this case, we're going to call our center C. All right, so if we have a segment or chord that has endpoints on the circle, and it goes through the center, that's going to be a diameter. So in this case, in this particular example, we have a diameter, and we're going to call it segment AB. So you have to forgive my handwriting here, guys. I'm using a mouse to do this. So segment AB. Now, we're going to put this right above it to signify segment. Now, some of you may remember, some of you may have seen, if there's just that piece above AB right up here, that means segment. If I put little arrows on the end, like so, that means line AB. Or if I put, erased everything. If I just put an arrow on one end, that means array. All right, but here, because it's a segment, I'm just going to call it segment AB, and I'm going to put that piece over it. All right, so that's a diameter. So it's, again, a special type of chord, so segment AB, that goes through the center point. So it's chord or diameter AB. Now, a radius actually is part of a diameter. Some of you may know what a radius is. A radius is going to start from the center point and go to any other point on my circle. So in this case, you notice we have 3 blanks here. We're actually going to have 3 different radii, which is the plural form for radius. So the first one we're going to have, we'll stick with blue. All right, so the first one we have goes from point C, which is my center, to point B. All right, so that's going to be my first radius. So it's still a segment, it's got endpoints. So first one, guys, we'll call segment CB. Again, forgive my handwriting. All right, so another one that we're going to have, still from the same center point, from C to A. So that's going to be another radius. So we'll call it CA. And then the last one, see if you can find it real quick. From my center point to point D. All right, so CD, segment CD is also going to represent a radius. All right, now you can also draw a lot of other ones, a plethora for a good vocab word for you, a plethora of other ones. That's a radius, that's a radius, that's a radius, that's a radius. Before we know it, we've got ourselves a little bike here. But those are going to be your radii. Anytime you go from the center point to another point on the circle, that segment would be considered a radius. So let's just kind of erase that and let's go on and look at some other ones. Now, sorry about that. Chord. So if we go back and think about what we saw with a chord. So a chord is a segment whose endpoints are on the circle. All right, so if we look at our picture here, I'm going to go, let's use red this time. All right, so I'm looking for a segment, so it's not a line or anything like that. So if you look down here, line L, this is actually a line, so we're not doing that. But it's a chord, so we're looking for a chord whose endpoints will touch the circle twice. So if we look right up here, segment KL right here, I'm trying to draw a straight line. All right, this segment right here is a chord. Its endpoints, notice K and L lie on the circle, and it's a segment. So that is one of my chords. So it's segment KL. Now, if you look at your picture, you might not be able to find the other chord. However, we've already actually named it. If you guys go back and look up at diameter AB, if you remember earlier, we said the diameter is a special type of chord. So in this case, my other chord, notice I got a second blank there, my other chord is segment AB. Now, we wouldn't call that a chord. We want to call it by its most specific name. And in this case, it's going to be diameter AB. However, this is also a type of chord. All right, so tangent line. So if we go back and look at the previous page, previous slide, a tangent line is a line that intersects my circle only one time. Now, it could be a ray, it could be a segment, but it only hits my circle one time. That's the key here. So we already named my chords, we named my radii. So this piece right down here, let me erase my other lines for you guys real quick so we don't get too confused. All right, so we're gonna go green now. So in this case, this right here, this bottom line down here is going to be my tangent line. So there are a couple different ways you can name a tangent line. One of them, you can name it by a single letter. Another one, you can name it using 2 letters. So in this case, we're actually going to call this line L. So we can say line L, like use a cursive L. Or you can say this is line MD. So just like we name a segment, we can also name a line with 2 letters. So you can call it line MD, or you can call this line L. Either way, it's going to be the same name. So line L or line MD. So that's my tangent line here. Now my point of tangency is that point where it's going to hit the circle once. So in this case, my point of tangency is going to be point D. So those are just some basic practices looking at some basic characteristics of a circle and some of the pieces inside the circle. So what I want you guys to do now is I want you guys to take about a minute or so and go through and see if you can't identify what type of pieces these are. So take a quick second and do that. All right, so what we're going to do is we're going to go through each of these and just see if we can identify the type of segment each one is. So let's look at this first one. So HG. Now it doesn't have anything above it, so we don't necessarily know if it means line HG, segment HG, ray HG. We can just come over here and look at our picture for that. So HG. So if we look at HG, which is going to be right here from H to G, notice it's got two endpoints. So this is actually a segment, so we're just going to put that little thing over to signify that it's a segment. All right, so let's look at how many times this segment touches the circle. All right, so if you notice, HG touches the circle once right here, and it touches a second time right here at E, which means it's either going to be a chord or it's going to be a secant. All right, so the way we differentiate between those is, remember, a chord is actually going to stop on the circle. Its endpoints are on the circle, while a secant touches the circle twice but keeps going. So if we look at this, just by looking at point H and point G, if you notice, those are both outside the circle, which means they didn't stop on the circle, they kept going outside the circle. So segment HG touches the circle twice but keeps going. So segment HG is going to be a secant. And again, forgive my handwriting, I'm doing this with the mouse. So that's going to be segment HG. All right, so it's going to be a secant. So let's look at the second one. YE. So YE, so let's kind of highlight this right here. So here's YE. Ooh, not bad. All right, so again, we want to use the most specific term that we can. All right, so if we notice YE, it's a segment again, so we'll put this little segment piece right above it, segment YE. All right, so it's a segment, so we know it's got endpoints, and if we notice the endpoints happen to lie on my circle, so it doesn't keep going outside my circle, it actually stops on my circle. So in this case, this is going to be a diameter. Now you could also say it's a chord, but this is a special type of chord, this is a diameter, because it goes through the center point of my circle. So we notice, guys, here, point C, that is my center point. So let's look at the next one. So it's FD. So once again, it's a segment, it's got endpoints. So there's segment FD. So if we look at the endpoints, we notice that the endpoints happen to stop on my circle. It does not keep going. So this is probably going to be a chord. But let's just make sure it doesn't go through my center point. So point C over here, that's my center point. FD does not go through my center point, so it's not a diameter. But in fact, it's a chord because its endpoints stop on the circle. So we'll put a chord here. Hope you guys can read all that. There we go. All right, so let me just erase a couple of these just so we don't clutter up my picture too much. All right, so the next one, if we look at CE, all right, so we'll go green. All right, so segment CE. So we start right here at my center point, and I go to some point on my circle. So if you guys remember back when we were talking about some of these basic characteristics, we said a radius is a type of segment that starts at the center point, so starts right here at C and goes to any point on my circle. Now I could go C to E, I could go C to F, I could go C to D, C to Y, C to B, any other point on my circle from the center point, that would be my radius. And again, there we go. So radius, and that's again a segment. And the last one we'll look at, guys, is going to be, erase that again. All right, the last one we'll look at, go back to blue, green might not be too easy to see. All right, it's HA. All right, now if we look, once again, HA, right here. Now, if you notice, and I marked it too much to where it might be harder to see, if you notice, that segment touches my circle only one time. All right, it's outside my circle except for that one spot right there. So if you remember, if a segment, line, or ray touches the circle one time, that is going to be my tangent. Now, it doesn't ask for the point of tangent C, but if it did, we would say that the point of tangent C is point B. That is the spot where that line, segment, or ray touches that circle one time. Now, what we are going to do from here is we're going to talk about a couple theorems. Now, these theorems don't actually line up. So when you see theorem 6.1 right here, this actually does not line up with your book. This is from a previous book, but we'll call it Theorem 6.1. You don't have to worry about remembering this is known as Theorem 6.1. But just make sure you know the premise behind this theorem. All right, so Theorem 6.1, I know you guys can read, but I'll go ahead and read it through with you. It says if a line is tangent, so if a line is touching a circle once, so if a line is tangent to a circle, and we're just going to highlight that because that's kind of the key piece here. If a line is tangent to a circle, then it's perpendicular to the radius. Now, if you go back and remember what we've talked about with perpendicular, that means two lines or two segments are intersecting at a 90-degree angle. So if we come over here and look at my picture right over here to the right, it says if a line is tangent to a circle, so right here I have line M. Notice it's tangent to the circle right here at point P. So point P would be my point of tangency. So we know line M is tangent to my circle, which means it's going to be perpendicular or intersect my radius at a 90-degree angle. All right, so notice right here I've got my 90-degree angle. So that's what Theorem 6.1 says. It says if I've got a line that's tangent, then it's perpendicular to my radius. All right, now we've also can talk about the converse. And if you remember what we've talked about with converse, that means you're flipping your if-then. So if you guys go back and look up here at my original statement, all right, this is an if-then statement. So converse means I'm taking my if and my then and I'm flipping them. So if my original theorem said if my line is tangent, then it's perpendicular to my radius, the converse would take that and it would flip it. So the converse says if I know a line is perpendicular to the radius, that means it's tangent. All right, so that's going back and saying, hey, I know this is a right angle, which means line M is perpendicular. So you can use both of those. So that would be the converse of that theorem. Again, you don't necessarily need to know it's Theorem 6.1, just know the premise behind it. So let's look at a couple of examples. All right, so this first one it asks, is BC tangent to circle A? Now, if you notice, they've given us three segment lengths. So they give us an 11, they give us 43, and they give us 45. Now, if you notice, this makes a triangle. Now, we don't know if it's a right triangle. It looks like it very well could be a right triangle, but we don't know that for sure. So, if you think back, go back in the files in your brain, think back of some kind of equation or something you guys have learned when we're dealing with a particular right triangle to see if something is a right triangle. And it kind of gives you this little hint right up here in the example. It says use the converse of Pythagorean theorem to verify a line is tangent. Now, if you guys go back and remember, Pythagorean theorem, good old Pythagoras, we got a squared, we got our b squared, and that should equal c squared. So that's my Pythagorean theorem. So we're actually going to use that to determine whether or not this is tangent. Because remember, if this is tangent, that means it's perpendicular to my radius. So AB is my radius. So if this is tangent, that means this is a right angle. If that's a right angle, that means Pythagorean theorem should hold true. So what we're going to do is we're going to use these values to plug into Pythagorean theorem. And if it's true, if my left side is equal to my right side, that means that BC is perpendicular to AB, which means it's tangent to my circle. So that's what we're going to do. So I'm going to take this, I'm going to move this up a little bit more, so get a little bit more room. So let's look at this. So remember, A and B, those are going to be the legs of my right triangle. Now, your C value is always going to be your hypotenuse, which should always be the longest side of your right triangle. So again, we don't know that this is a right triangle. What we're going to do is we're going to assume it is, and then we're going to plug in my values here. We're going to plug my values into the Pythagorean theorem to see if it works. So AB and BC would be my legs. So that would be little a and little b. So we're going to say, we'll just say A is 11. You can say B is 11, but this is arbitrary how I'm going to do this. So 11 squared plus, we're going to say B is my other leg, so 43 squared, equals, remember C is your hypotenuse. That should be the longest leg. So 11, 43, 45, obviously the biggest number is 45, so that should be my hypotenuse. So we're going to put that right there. All right, so what we're doing is we're checking to see if this side is equal to the right side, the left side equal to the right. Because if it is, that means once again that this is a right triangle, which means BC is perpendicular to AB, which means BC is tangent. So that's what we're going through. So 11 squared is 121 plus 43 squared, and I actually got to grab my calculator real quick. To make sure I am calculating this correctly for you. All right, so we've also got 43 squared, which is 1849. 1849, that was a good year. Equals, all right, we're going to look at 45 squared, which is 2025, or 2025. All right, now, if we take and add up my left-hand side, if we add up 121 plus 1849, we get 1970, also a good year. Don't remember it, but it's a good year. So 1970, and I get on my right side is 2025. Now, if we look at both sides of my equation, 1970 does not equal 2025 or 2025, which means Pythagorean theorem did not work here, which means this is actually not a right triangle. So therefore, BC, I'm just going to write this as neatly as I can, BC segment is not tangent. Because remember, to be tangent, it has to be perpendicular or make a right angle with the radius, which means Pythagorean theorem should work. But because Pythagorean theorem did not work, that means it is not tangent. So if we want to pause this for a second, I want you guys to try that second one for me and determine whether or not BC is in fact tangent to AB. So hopefully you had a quick second to kind of go through and look. So remember, guys, we're looking to see if BC is tangent to AB. That means it makes a right angle with my radius. All right, so in order to determine that, we're going to use Pythagorean theorem to see if it holds true. So let's look at that real quick. So Pythagorean theorem, once again, we got it right over there. So A squared plus B squared equals C squared. So remember, A and B are my legs, or my two shorter sides. C is going to be your hypotenuse, which is your longest side. So A and B. So let's just say A is 7, so we'll go 7 squared plus 24 squared equals my hypotenuse, which would be 25 squared. That's my longest side. All right, so let's just go through and evaluate. So we know that 7 squared, if we plug that in, which hopefully you know what 7 squared is 49. We know that 24 squared is 576. There we go. There's a 5, there's a 7, and there's a 6. That's a 6, I promise. Equals, we know that 25 squared is 625. So if we add these up, we'll just make that look a little bit more like a 6. There we go. If we add those up, 49 plus 576, we actually do in fact get 625. Now, last time I checked, and it's been a while, but I'm pretty sure last time I checked, 625 is equal to 625, which means Pythagorean theorem worked, which means BC is perpendicular to AB, which in fact means BC is tangent. Ooh. BC is tangent to circle A. And typically, guys, when they name circles, they name them based off of their center point. In this case, A is my center, so that's why they call it circle A. So, there we go. We are almost done. All right, let's look at my last part here. So, another piece, so this is kind of the last theorem we'll look at, and then we are going to do a couple of examples with it. So, last part, again, theorem 6.2, you don't need to worry about knowing that this is theorem 6.2. I just wanted to make sure you guys know the premise behind it. So, what we've got here is it says if two segments from the same exterior point, exterior meaning outside, all right, so if we have basically two segments line arrays that intersect outside the circle. So if you notice line RS and line TS both intersect right out there at S outside my circle. That's that exterior point. If both of those segments are tangent to the circle and they intersect out here, then those two segments are congruent, which, like we've said many, many times this semester, that means they are equal to each other. So it says in this case, if SR and ST are tangent to the circle, they both intersect at S, that means that segment SR and segment ST are congruent to each other, which means they're equal. So if we're going to go through and solve for something, we're going to set them equal. So let's scroll down here, look at example 5. So it says use the property of theorem 6.2. Once again, don't worry about theorem 6.2, just know the premise, to solve for x. So they give us a couple things here. First thing they say is that AB is tangent to circle C. That's key. All right, we need to know that AB is tangent. So it's tangent. That's good to know. And at B, so it's tangent circle C at point B, and we know that line AD, this line right here, is tangent to circle C at point D. So both of these pieces are tangent to the circle. And if you notice, they both share point A, which means they are intersecting out here at point A. So if we go back and look up at my theorem, it says if two segments from the same exterior point, so both of these segments from point A, are tangent to my circle, that means that this segment right here, x squared plus 2, my segment AD, is congruent to segment AB, which is 11. So remember, congruent means equal. So that means that x squared, if I'm going to solve for x, that segment AB, x squared plus 2, is going to equal 11. Because AD should be equal to AB. So if we just go through and use our basic algebra skills, so let's subtract a 2 from both sides, because again, we want to get x by itself. So, nice straight line. So those are going to cancel there. So 11 minus 2 is 9. So x squared equals 9. All right, so from here, to get x by itself, anytime we have something squared, we want to get it by itself, so we take the square root. So I'm going to take the square root of both sides. All right, when I do that, the square root of x squared is going to give me x equals. Now, remember, when you solve, you want to make sure you include plus or minus anytime you take the square root, and then check to make sure both values actually work. So the square root of 9 is actually not just 3, it's actually plus or minus 3. And if you go back through and plug each of those values in, so we have a positive 3 and a negative 3, you plug both of them in, positive 3 squared is 9. 9 plus 2 gives me 11. They're equal. Same thing, if I go and plug in a negative 3, remember, anytime you square a negative, it becomes positive. So negative 3 squared plus 2 is also 11. So both of these values work. So my solutions are x equals plus and minus 3. And that is going to be it. We're actually going to get into these type of examples at some point later. So that's it. So those are just some basic properties with circles. That's section 12.1. It's being able to identify different segments and lines and rays inside a circle. So I hope that was easily understandable. Come back and look at this if you need to when you get home for homework, if it's going to help you. All right, you guys should have some practice to be working on for homework. Don't forget, Monday is a student holiday. It's a teacher work day, so you don't have to worry about being here. So you're welcome. Hope you guys have a wonderful weekend, and I look forward to seeing you guys when I get back. Thanks, guys.